Hello, I'm Shaumik and I'll be presenting our work Sinogram upsampling using Primal-Dual UNet for undersampled CT and radial MRI reconstruction. Magnetic resonance imaging or MRI and computed tomography or CT are two of the most commonly used tools in medical imaging. However, they come with their own distinct problems. MRI acquisitions are inherently slow, while CT scans expose patients to X-radiation. Subsampling can help solve these respective problems, but it leads to artifacts. Subsampling CT or radial MRI both introduces similar streaking artifacts. The aim of this research is to reduce such artifacts using a single deep learning method. Primal-Dual network, proposed in 2018, has been seen to be the best performing deep learning model for CT reconstruction, even in latest comparative studies performed in 2021. However, it might be slow due to the high number of iterations. This research aims to reduce the number of iterations while improving the reconstruction quality. Primal-Dual network proposed by Adler and Öktem can be interpreted as an unrolled iterative reconstruction algorithm that optimizes in both sinogram and image space using blocks of fully convolutional layers. Iterations alternate between primal or image space and dual or sinogram space. In a simple overview, going from primal to dual, forward projection is performed, while going from dual to primal, filtered back projection is applied. In our proposed model, we have reduced the number of unrolled operations from 10 to 2 to reduce the required processing time for repeated reprojection and filtered back projection. But to retain the computational complexity of the model, the primal space blocks were replaced with units. This modified network is called the Primal-Dual UNet. Here we can see the network schematic. For the CT experiments, we have simulated the fan beam projections of 28 subjects split into 16, 4 and 8 subjects for train, validation and test sets. For MRI experiments, we have used brain MRI from IEEE dataset with 185 subjects split into 100, 35 and 50 for train, validation and test sets, and abdominal MRI from Chaos dataset with 40 subjects split into 24, 6 and 10. Equidistance radial acquisitions were simulated for both these MRI datasets, and then one-dimensional inverse Fourier transform was applied on each spoke to obtain the sinograms. We have experimented with 3 subsampling factors, 4, 8 and 16. Normalization in the primal space was performed by dividing with the 99th percentile of the dataset, whereas in the dual space, z-score normalization was performed. Loss during training was calculated using the L1 loss and was optimized for 151 epochs using the Adam optimizer. We have compared our method against 3 deep learning baseline models, reconstruction UNet, sinogram UNet, and of course the Primal-Dual network. Here is an example result for fan beam CT with subsampling factor 16. We can observe that the proposed PD UNet outperformed all the baseline models. Here is another example, this time of radial MRI of brains with subsampling factor of 16. Here also we can see the proposed network outperformed all the baseline models, both qualitatively and quantitatively. We have also compared the processing time of the Primal-Dual network against our proposed Primal-Dual UNet. We can observe that the proposed model is faster than the original Primal-Dual network, and the difference becomes more pronounced with the increase in the number of projections. In summary, CT-inspired reconstruction algorithm for undersampled radial MRI shows promising results. Bilinear upsampling the radial MRI sinograms, then performing filtered back projection, already outperforms the conventional NUF reconstruction. The deep learning based techniques perform even better. All investigated deep learning models improve reconstructions of sparse or bilinearly upsampled sinograms. Primal-Dual UNet performs comparable or better than Primal-Dual network in most CT experiments and better in all MRI experiments. Further experiments have been performed for regions of interest and needle insertion. Now to conclude, a novel Primal-Dual UNet architecture has been proposed here which outperforms the baselines with statistical significance and generalizes better. It improves in terms of speed and accuracy. And also this research shows the potential of using Sinogram upsampling for undersampled radial MRI. The preprint of the full manuscript is available on arXiv, and the code of this project is available on GitHub. Thank you so much for your attention, and feel free to contact me for any questions or feedback.